Hello, welcome to the R lab for cross-validation in the Bootstrap method. We're going to start this lab by looking at the validation set approach, where we train on one subset of data and test on a separate subset. This is the method we've been using prior to cross-validation. After we talk about this validation set approach and try it out, we're going to try out some cross-validation. So to start with, we load in our Isler library. We're going to set our seed. So this sets the random number seed, so that when we take random subsets, we're going to get the same results that I would get on my computer and you'll get on your computer, and the authors of the textbook will have in the lab when they show results in the textbook. So the first thing we do is we create a training data. And so this is a subset of the training data. So we're taking a subset of the data, 196 samples out of the total of 392 that are available in our training data. And so now we're going to create a linear model that we're going to fit miles per gallon as a function of horsepower and working with the auto data set. If you ever want to get more information about a data set, you can type in question mark in the name of the data set. And if the data set's in R, you'll get information about it over here. So here's the auto data set. As we mentioned before, there are 392 vehicles in this data set, and then there's 9 variables, and then you can see miles per gallon, cylinders, and so on through the variables in this data set. Okay, so we'll train our linear model, and the subset here that we're going to be training on is our training subset that we created. Now we're going to attach auto so that when we create things, we don't have to use this data equals auto every time we make a command in R. And now we're going to use that data, that linear model that we just used, we're going to fit it to the auto. We're going to take the difference between the miles per gallon and the predicted miles per gallon, and we're going to only look at the data for that minus the training data. So this says we're going to take our linear model, apply it to the test data, and compare the test data compared to the actual miles per gallon. And then we're going to take that difference, and that's the error, and then we're going to square it and take the mean. So this will give us mean squared error on our test data. So our mean squared error is 26. Then we're going to make another linear model. This time we're going to make a linear model that uses a polynomial of horsepower, and it's a degree 2 polynomial. And we're going to create this linear model on our training data. And there's our mean squared error. Mean squared error, you can see, is dropped from 26 down to about 19 or 20. We can make a third degree polynomial linear model using a third degree polynomial of horsepower. So this means that the predictor variables will be horsepower, horsepower squared, and horsepower cubed. When we look at the fit from that, it's not significantly better than the second degree polynomial. So let's go through and do the same things again, but with a different seed, just to see how reliable our results are if we change the seed. And so we see that drop from the linear model here. It gave us a mean squared error of 23, dropped down to 18.9 when we took the second degree polynomial. When we do a third degree polynomial, it's back up to 19.2. Not much difference between 18.9 and 19.2. Not a significant difference. Those are about the same, but we get a drop in error when we go from linear to quadratic. Now we're going to use the leave one out cross-validation approach, and we're going to go through the same process of looking at these linear versus quadratic versus cubic models for miles per gallon as a function of horsepower. Here we're using GLM. Above we were using linear model. GLM is generalized linear model. If you don't specify the family, it's just going to be using the linear model, but it has some other factors, particularly the working with the cross-validation, which we'll get from the library boot that works with GLM. So we're going to look at the coefficients from GLM, and just to confirm that using GLM fit gives us the same results as linear model fit. We look at the coefficients, and they match. The intercept is 39 out to decimal places. Horsepower coefficient, it matches out to a few decimal places as well. So let's use the boot library. and will fit our generalized linear model, and this is just horsepower. And then we can compute the cross-validation error. Cross-validation error, the delta gives us the cross-validation mean squared error, so 24.231 and so on. You can look into this and see, the difference between these two numbers, but that's giving us the mean squared error using cross-validation. So cross-validation error, we're going to make a vector of length 5, and what we're going to do here is we're going to do a for loop. So this initiates our for loop. I is going to go from 1 through 5. These commands inside the curly braces are going to be executed through the loop, and I is what we're iterating on, and so I is going to be the degree of our polynomial, and then our cross-validation error is going to be where the cross-validation error from that for that degree I model, where it gets saved. So let's execute these commands. Takes a moment because we're doing leave one out cross-validation, 392 vehicles, so we have to do 392 linear or quadratic or up to 5th degree polynomial models in each of these cross-validations. And then we're doing 5 of those, so it's 5 times 392 models that we had to construct. And then we can look at this vector that gives us the errors, and we see the linear model had an error of about 24, and then using cross-validation, we see quite robustly that there's no improvement as we increase the degree of the polynomial in our regression model. So this is one of the things about cross-validation. It's 19.2, so on, 19.3, so on, 19.4, so on, 19.0. This is a much flatter representation of the lack of increase or decrease or much of a change in our mean squared error in comparison to what we got previously. We got 23, it dropped down to 18.9, 9.2. There's a little bit of fluctuation here. And again, here when we used a different random number seed. So those look like there might have been a little bit of change. We didn't think it was enough to matter. Cross-validation gives us a more robust measurement that we had a drop from 24 down to 19 and then very little change after that. Not a significant change after that. Thank you very much.